say we still try in illustrated. Okay, so here I want to try without giving the rules first. Okay, just try using our fundamental complex algebra to see how much we can do about the drawing the transfer function. So we consider this example here. K as s plus 1, s plus 2. Okay, so for this case, we want to determine the y over r will be equal to, let me call this is g. Okay, so that is gs and 1 plus gs. So the characteristic equation is 1 plus gs equal to 0. So which means 1 plus k, 1 s plus 1, s plus 2 equal to 0. Okay, so this is a 1. So the root locus, again, here we recall what is the root mean. The root locus is meaning the collection of the points satisfying the characteristic equations. Okay, so that means this is our starting point, exactly that fitting to the standard form. So we don't need to do any revision of the form. So basically here the root locus is to find out the collection of the complex number that is the root of the characteristic equations. And how come we're going to have a collection of the points? Because here we're going to k is a parameters, so k is changing. Okay, depends on the needs of the design. So here, because k is parametric, that makes the things happen. That is, we have so many possible roots. Okay, so we want to collect all the possible number of the roots. So that is a starting point, and fit these equations back to here. Back to here, our point we're starting is this one. So again, we follow this concept here, and let me rewrite. And here we have two criteria. One is the magnitude, and one is the phase criteria here. Okay, so let me do this way. The magnitude criteria, and for this case is this. Okay, so for this case again, here let me put certain restrictions. Here we only consider is in the design domain k is non-negative. Okay, and then here is the phase. For the phase criterion, so basically here I think I skipped one step. So here let me rewrite here. Okay, starting from there, then we applied this criteria here. So the phase criteria is okay, L can be any integer, positive, 0, or negative integer. So this is our starting point. So with this one, let me erase this portion. from this drawing, I'm going to combine our knowledge from the 2 lecture hours earlier. And in that 2 lectures hours earlier, we have tried intuitive drawing of simple functions. Okay. So if you remember, I will try to get everyone to remember it again. The steps is not the steps are not fixed, okay, and sometimes we can jump in around among the steps, okay. So which means I call this a steps and not procedures. Okay, procedure we have to follow step by step accordingly, but step we can jump in around. So basically here we try to piece by piece and collect all the information. So here, let me put these things very big. Let me put the bigger one. Yeah. Here we're working on is on the complex plane. Okay. The step 1 is to identify. Locate Okay, so for this example, the QS, TS is given by 1 s plus 1 s plus 2. So for this case, and here we have no zeros. Okay, for this case, here we have the poles at 0 and -1, -2, right? And actually, I would say no zero. That means the zero locate at infinity. So that is obtained from our intuitive exercise last time. Because for this case, before we proceed, let me ask you, how many branches of the root loci will have in this example? 3. 3 branches, because here we're looking for the highest degree of the polynomial. This is 3. So looking for 3 branches. And we also know that the root loci will start at when k equal, let me label the poles first. Okay, so the pole is here, 1 is 0. So using cross mark, and here is 1, here is 2. So -1, -2. Okay, we're using cross mark for poles, and here, let me label it. So here we're using cross mark, and 0 is we're using 0. Okay. So we know from last time, and we know the root loci starting at poles, and that corresponding is corresponding k equal to 0, right? Okay, so this one, you need your kind of turn over to the previous lecture notes. And so the root loci starting from k equal to 0, and then we'll do transit in certain way, and then 3 branches will be ended up at zeros. Okay, so poles here, I would say this is the starting point. Pole is the starting point of root loci, and zeros basically is the ending point of root loci. Okay, so in the finite range, if there's no zeros, then we for sure they must be infinity. such that the 3 branches will be ending up there. Okay, so that is the first step. And so now we have the starting point. So the next step is we want to determine the portions of the root loci, possibly on the real axis. Okay, so because you see the root loci will distribute in a certain way, maybe sometimes on the real axis, we don't know which portion yet. And then once they break out, then they will go away. Okay, and then so the always is we try from the easy part. Easy part, that means it's only associated with the real number. So the next one is to determine the portions of the root loci and or root locus. Sorry, I'm not allow me kind of the mixed building the single or plural terms here. Okay, the real axis. Okay, so right now the real axes are divided into 4 portions. One to the right of the 0, 2, 3, 4. 4 segments, and we can determine which segments are in. Okay, and can we try these segments first? Okay, don't ask me why, but I know the answer already. So we try the answer first. Okay, we try this segment first and see what happens. And how do we test this segment will be the part of the root loci? Any way we can do it. So in this segment, that means the number of the S is between 0, -1, and 0. How do we know the collection or this range will be part of the root loci? Anyone has any idea? This one, right? As long as any number of S satisfy the both criteria, then that S is part of the root loci. Okay, so we see. So right now we have the S here. So say we try this point. Let me put a test point here. If you have a color pencil, do it. Okay. So here, let me put a test point here. Okay. And we check the phase criteria first. Okay. The phase criteria is what? Is this one. Okay. So let me. What is this one? Do the calculations. So basically, the phase criteria here. Okay. Let me do the calculations. So by the phase criteria, and let me rewrite. Basically, that is this 1 S plus 1 S plus 2, and that one is equal to, on one side we can do the calculation. Basically, is the phase of the numerator, which is 0, minus the phase of the denominator, which is S. Right? Good. On the other side, this one is minus 80 degrees and plus minus 360 degrees times n. N is any numbers. Okay, so that is one. So now we check this one. So now this is the one I'm going to graphically join on here. So in particular, I want to determine first is what is this one? And what is this one? What is this one? Okay, so I'm going to draw it on the graph here. What is angle of S? What is that one? What is this? That simply means the angle between S and origin. So basically here we're connecting to here. That is this angle, right? So this angle is how much? We do it 180 degrees, right? Okay. And the second one, what is S plus 1? Again, right now we gradually kick into our fundamental properties. This one representing is the angle between the vectors of S and minus 1. So that means it's this, right? Is that vectors. And for these vectors, and that has pointing to there, so what is this? This is 180 degrees. This is 0 degrees, right? Can you tell? Because this is our real part, imaginary part. So here, if this is S here, and here is minus 1, simply this vector representing is S plus 1 vectors, right? And under this case, you can see that is has a phase angle 0 there. Okay, so that's 0 degrees. Then, so this is 0 degrees. And S plus 2, the same thing, that is these vectors. Again, this one you can easily, similarly, as 0 degrees here. Okay. So by plugging into this calculation, you can see the left-hand side exactly give us is minus 180 degrees. Voila, that's satisfying. So in this way, by changing the S, as long as this testing point is within this domain, this range, this segment, then the calculation won't change, right? So that means, so let me label it. So that means this will be part of the root loci. Okay, be good? And my exercise is this one. So from here, we keep that good drawing. So we can try so 0, minus 1, minus 2. And we can try this segment here. Okay, the second segment, we try this segment here. Okay, so we give a try again. So for this one, this calculation in this segment, S equal to, again, that is S, right? Equal to 180 degrees, right? And then we try S plus 1. S plus 1 simply is this is S, this is 1, so this is S plus 1 vector, right? So this one is 180 degrees. And then S plus 2, so this is the vector S plus 2, so that is 0 degrees, right? So we plug in here, so that is 0 degrees minus 180 minus 100 plus 80 plus 0 degrees. So from this calculation, we see that is a minus 160 degrees. By all means, by no means, doesn't matter how we choose to aim, this always won't satisfy. So this one we prove this segment is no. This segment is not our answers. Be good? We keep playing. If you like, you can keep playing. Right now, for the remaining, we haven't tested this segment, but you can keep playing. The procedure is the same. Keep playing, that means you check the criteria there. You good? You okay? So now let me clean this drawing. Or you can plot you can make a new plot. Okay, so you can make a new plot. Let me make a new plot. So this is a part of the root loci. and this is a part of the root loci. Okay? And we identify the two segments on the real axis is simply check against the phase criterion. We haven't used the magnitude criterion. Okay, the magnitude criterion will allow us to determine at which location what is the value of k. So, for example, say if you like to say, we can say s equal to minus 0.5 here. Say equal to minus 0.5. Okay. So if you want to know what the value of a k at this particular point, how you can do is simply plug in s equal to minus 0.5 into this calculation. We can do a try. Okay, so s and plug in s equal to minus 0.5, so that is minus 1/2, and minus 0.5 plus 1 is 1/2, minus 0.5 plus 2 is 3/2. Okay, so that number is equal to k over 1 over k. So in this way, k equal to how much? The magnitude of the whole thing is 0.375 here. Good. Okay. So in this way, the root locus starting from the pole, so starting from here, and that corresponding is k value equal to 0 and k value equal to 0. So say when s equal to minus 0.5, we know our calculation k equal to 0.375, etc., etc. Okay, so that means say if you want to exercise the value of k here, and say s equal to minus 5, repeat the same procedures, you can determine this value as well. Okay, so the root loci will starting at here, so k equal to 0, and this is the increasing trend of the value of the k going there. So the next time we're coming back, we see how the root loci will, how to say, take a breakaway and get into occupy with the imaginary part there. Okay, so this is step 2. Then we will continue to add it up more and to complete this drawing. Okay, thank you.